Hello, and welcome to ANNSIM. I am Dr. Michael Grieves, the Chief Scientist and Executive Director for the Digital Twin Institute. And based on the agenda, I think you're in for an exciting program over the next couple days. What my job here is to set the stage for an overall picture of digital twins and the foundational role that modeling and simulation plays in that. My topic is digital twins, utilizing modeling and simulation to drive 21st century transformation. This is the original digital twin model that I introduced in 2002 when I was at the University of Michigan and had worked on it during my doctorate at Case Western. The name it had was information mirroring, which was not nearly as dynamic as the digital twin name, but it really was the conceptual ideal for product lifecycle management. It was first introduced at a Society of Manufacturing Engineers conference in October, and then at a PLM center we were organizing at the University of Michigan in December. It has the same elements except for the sub-elements down in the below right-hand corner that called out the fact that we could have multiple virtual spaces, and that was not very well known at that particular point in time. This is the digital twin model as it exists today, and it has the three main elements that I contend consists of digital twins. On the left-hand side, it has the physical products and the physical space that we've had since time immemorial, and quite frankly, have pretty much had to work in this space exclusively. As soon as we had an idea for a product, we had to turn it into physical form in the form of drawings, blueprints, physical prototypes, so that we could share it with other people. On the right-hand side is this idea of virtual or digital space, and this consists of the digital and virtual elements of both the product and the environment that that product operates in. The third aspect is this idea of connecting the two spaces, the physical space and the virtual space. And what we have is we need to take data from the physical space to populate our virtual space. And then we want to be able to use that information over in the physical space to provide value. And I'll talk about what kind of value that provides in a few seconds. Why do we want to do this? We want to do this because we want to move work activity from the physical space that we've operated in from the 20th century and before to moving as much work activity as we can in the 21st century to this virtual space. And why we want to do that is we want to substitute information for wasted physical resources. So what are the characteristics of this physical world we've lived in since time immemorial versus the digital virtual characteristics? So I can look at a number of things where we differ pretty considerably. In the physical world, we have to use atoms, and that's a constrained resource. Cost us a lot to work with atoms. Where in the digital virtual space, we work with bits, which is a pretty unconstrained resource, and in fact gets unconstrained more each and every day as computing capability increases. We only have a single space to work with in physical space. There's only one world that we're aware of. I know you alternate universe people are going to argue with me, but for right now, I'm going to contend that we only have a single space to work with. In the digital virtual space, as in fact I showed on my conceptual model, we have an infinite amount of spaces that we can work with in the digital virtual world. Physical space requires sequential proximity. We've got to be near the physical thing that we're looking at and working with in order to have the information about it. Where in digital virtual space, we can have simultaneous access to it no matter where people are, and it doesn't require sequential proximity of the people. They can be anywhere in the world and still have access to that information. The physical world is time-lagged. Not only do we have this idea of sequential proximity, but we basically spend time having to move things around physically, whereas in the digital virtual world, it's instantaneous. And then finally, there's a low trade-off for physical waste and information, and a high trade-off for physical waste and information, as I'll talk about in the next slide. The discussions about what information is marked by a lot of disagreement and confusion. And I'm not too concerned about defining what information is. What I wanted to know is, what does information do? Where do I get value for information? And in life, pretty much all of our activities and tasks are what I call goal-seeking activities that minimize the use of resources. And my contention is that information is a substitute for this task wasted time, energy, and material. So if I look at the bar on the left, I can take any particular task and divide it up into two areas. The green part is the most efficient and effective use of resources. If I was omniscient and omnipotent, this is the only amount of resources that I would use to complete the task. Everything above that is what I call information inefficiencies. So whether it is developing a product, manufacturing the product, or figuring out how to repair the product, or even something simple as how to figure out how to get 3 kids to their after-school practices, this idea of having a task that has the most efficient way possible and information inefficiencies is what we deal with. We can cost that because we live in a capitalistic society, and we can cost the time, energy, and material. On the right side is my idea of information as a substitute, not for the physical resources that we need to perform the task itself, but for the information inefficiencies. And as I'm showing here, I'm replacing all of them with my information, and that will never happen. We are not perfect in the human world, but even if it replaces a small amount or even a larger amount, it's going to be very beneficial for what we're doing. The problem is that we have a tough time costing information because we don't have a unit of measure like we have for time, energy, and material. But we can get to there with a proxy in terms of the cost of hardware, software, and people's time to, in essence, create this information. Where this works is if the cost of the information is going to be less than the cost of wasting the time, energy, and material and information inefficiencies. So for simple tasks, we don't necessarily need information, but for the complex tasks that we're faced in today's world, and that certainly when they're repeatable, that the idea of creating information for information inefficiencies is very effective and efficient. And that's why I will contend that those of us that are living in the computer industry have done well over the past few decades. The substitute of information for wasted time, energy, and material has only increased over time as the computing capability has increased. All of you should be familiar with Moore's Law, which is this exponential graph of the advances in computing, with computing capability doubling approximately every 18 months. And so we start off in the early 70s at 2K chips, and we have recently gone past 80 billion transistors on a chip. And what's sort of interesting is how this is dramatically increased. I worked on the first supercomputer, the Iliac 4, in the early 70s, and we had 25 megaflops of capability out of that on its best days. And the size and consumption of energy and air conditioning was pretty phenomenal. Very, very large, and took up an entire facility out at Moffett Field. Today, you can get an Xbox that has 12 teraflops of capability and in a form factor that fits under your desk. So this has dramatically changed the ability of trading off of bits for atoms, and the cost of bits keep getting up. As you note, inflation is going up pretty dramatically, whereas the cost of bits is going down at this exponential rate. I usually show the logarithmic graph, but it gets a lot more impressive when you look at a linear graph of the advances in computing, as I've shown in Moore's Law in the previous slide. We've reached the inflection point, and we are pretty much getting asymptotic with respect to the y-axis. And so this shows that around the 2011, 2015 range, we started to go up dramatically, which I will sort of contend is why digital twin capability started to take off. We started to be able to do what I had projected we could do in the early 2000s. What's kind of interesting is that if I look at the projections, we are in for huge amounts of increases. In 2030, 128 times increase in capability, and by 2040, a 16,000 times increase in capability. There are some that say Moore's law is decreasing, but these are still pretty substantial increases in either transistor density or equivalence. What's also interesting is if I look at the amount of publications on digital twin, it correlates in this particular area and also is growing exponential. Now, this is not causation, it's correlation, but it shows that I think that we have reached a point where we can start to realize the kinds of capabilities that we need for modeling and simulation and AI in order to be able to do actual digital twins. So what's happening in terms of the digital twin model in terms of scope and scale? I had first proposed it being for tangible products because I thought that was easier for people to understand. I looked at the areas where it was being involved in, and it was automotive, locomotives, power generation, airplanes, spacecraft, ships, ports, and oil rigs. We also are seeing it in smart buildings, even the development of vaccines for COVID, and the digital twins of oceans and the earth. Clearly, the idea of the digital twins of people is something that we're starting to see a lot of activity with. And so digital twins scope and scale is exploding in pretty much all areas that you can think of where it's a tangible thing in the physical world. However, there's no reason that the digital twin model can apply to intangible things. If I can visualize it, I can create a digital twin of it. So we're starting to see digital twins in logistics, the process industry, whole economic systems, certainly manufacturing processes, and then in the supply chain, which I have talked about as being a supply net, which is the counterpart of the supply chain. So digital twin models, if I can visualize it, I can create a digital twin of it, even if it's something that is relatively intangible. From its very beginning, the digital twin has always been intended to encompass the entire product life cycle. And we were moving from a functional centric perspective of engineering, manufacturing, servicing, to a product centric where we were going to populate and consume throughout the entire life cycle, as I'm showing in this little diagram below. And I divide the product life cycle into create, build, operate, sustain, and dispose. But that means that we need to have different digital twin types that will encompass the entire product life cycle. And those types, there are three types that I've defined for digital twins. The first is a digital twin prototype. And as you can see from the picture, it starts with an idea, very, very fuzzy. And at the end of the create phase, I have a fully formed product and the means of production of how I can produce that product. So these are all the products that can be made. And this is all the data and information that's going to allow me to take that right side product and actually start to create specific instances of that product. At that point in time, it has specifications, they have tolerances on it, so that I'm basically saying that these are how we can make the products, and if I make the products within these tolerances, they're going to perform the way I need them to perform. When I start to make products that are complex, and I want to create a digital twin instance of each of those products. In this particular case, it's an F-35. I need digital twin instances for complex products. I certainly don't need a digital twin instance for simple products like paper clips, but when I start to move into the complex products that we're seeing today, airplanes, nuclear reactors, medical devices, and certainly all these sorts of these complex products, I want to have a digital twin instance. So it doesn't have a tolerance anymore. It has a specific measurement that I measured during the manufacturing process, and it has quality control information of how I was able to ascertain that this met my design. And so these digital twin instances are basically connected to the product. They're the as-built of the product, and they're intended to connect to that product throughout the entire life and being able to reflect what that product is going to do as it goes about in the world. These are all the individual products that are made. But one of the real values is if I can take all these digital twin instances and collect that information so that I can start to do correlation and ideally causation that says when I see these particular aspects of the product, these sensor readings, I can predict the product performance. So I can start to predict failure of componentry or failure of the product to keep performing the way it is. These are the digital twin aggregates. And these are all the products that have been made. And so these are the three types of digital twins. The digital twin prototype that starts the create phase. I create a digital twin instance of it. And then I have a digital twin aggregate because the more of these things that are out in the world that I can capture the information on, the better prediction and machine learning I can do about how they perform. And so this is the digital twin types that sit there underneath the digital twin. And I use information, for example, from the engineering intent in the digital twin prototype to inform myself during the operation of the digital twin and being able to use that in order to be able to ascertain how that product is going to perform and predict failure. So I'd like to show you how the digital twin model works throughout the entire life cycle. And during the create phase, as I said, you have the model as it's shown in the simplest form, where I have physical space, virtual space, and the connections between that, which is often called the digital thread. Not my fond term because I've hung on by a thread too often in my career, but it is the nomenclature we're stuck with. I would like digital pipe, digital I-beam, but the digital twin is this communications mechanism. It does not contain information. It merely allows me to connect to the different repositories and pull that information in. But in the create phase, I also need to create the means of production. It doesn't do me any good to create a digital twin, an engineering drawing, if I can't make it. And so I have to, and then in essence, create the means of production, the instructions for the various machines that allow me to pour in raw resources at one end and come out with a physical product at the other end. I use my digital twin prototype at this particular phase. When I start to build it, which is probably the most complicated time during the product life cycle, is what my intent is to do is to be able to create physical products on the left side that mirror the digital product that I've created during the digital prototype phase. And what I do is then I use that information that I created about the means of production in order to create and guide the digital twins of the machines that are going to make this product. They send it to the physical machines, and then I create the physical product. But I want to capture that information over on the left-hand side for the digital twin instance that I'm going to have. So I use the prototypical digital twin, and I use the digital twin instance at that particular phase. When I go out and sustain the product, I now have the digital twin instances that I want to track throughout its entire life and be able to have the information about that product. No matter where that product is in the world physically, I have its digital twin to be able to have the information about it. So I'm going to use the prototypical digital twin, the information about how it's supposed to operate, the instance that I created that I'm going to change over time, and ideally I want to create the digital twin aggregate that is going to allow me to do such things as prognostics and performance prediction. One of the things that this is allowing me to do is to connect back into the create phase with this information, because too often I see generation after generation of a new product that basically has the same problems as the previous generations. Why? Because nobody's told the engineering people that what they assumed was going to be the performance of the product isn't. So tying this back is going to allow me to create better products in new variations of that product or new generations of that product. I want to spend a few minutes talking about a fallacy that I've come across, in fact, many times, although it seems to be decreasing a bit, is that the digital twin requires a physical counterpart fallacy. And this is the idea that until it rolls off the factory line, there doesn't need to be a digital twin. But that is a major fallacy, as I should have convinced you about, where the fact that when I'm in the create phase, I start with a digital twin first. I would really like to design my product, test my product, manufacture my product, and support my product all digitally and make all my mistakes there before I ever move around expensive atoms. But the digital twin framework should cover the entire product lifecycle. That's what the intent of it was right from the beginning, that it basically covers the create, build, operate, sustain, and dispose phases of the entire product lifecycle. And in order to have a product-centric view of the world, it needs to do that. The digital twin always exists prior. In some organizations, they're just trying to call it by a different name. And so this idea of having a different name for the digital twin, I think, goes back to driving functional centric perspectives. And it's not just semantics. How we talk about things is how we think about things. And so it isn't simply, well, I just have a semantical difference here, a difference in the naming. It is basically the idea that I'm going to think differently about it when I have a different name for things. And as I alluded to before, it does regress to being functionally siloed. I mean, if the engineering people have their own certain thing that's not a digital twin, they don't feel that they need to share it with the rest of the organization. And again, I want to drive to this product-centric perspective so that I'm looking at the entire product lifecycle in this virtual capability. And finally, I will contend that it's conceptually inelegant and piecemeal to have different names for different things. I can have different types, as I've shown you, but I ought to have it underneath the entire digital twin concept. The digital twin in time looks like this. If I look at below where I have my physical world and the top where I have my virtual world, I have my physical things at time 0 plus x. And every time at 0 plus x, what I like to do is to replicate what's happening with that physical thing in its digital twin. So I want replication. In a factory, I want to be able to know what's happening over the entire factory without having to walk from machine to machine. And so replication is the first aspect, the ability of replicating this information and being able to have instantaneous and simultaneous access to it. But one of the really big opportunities is what I call front-running simulation. And this is at the idea that every time 0, I'm going to run a new simulation that is in essence going to be my crystal ball into the future. So if I have a glitch in a robot at time 0, I'd like to know that 2 hours later that there's going to be a bottleneck and go fix it right now rather than waiting for that bottleneck to occur. So this idea of the digital twin in time is this idea that not only do I have a replication that I can see what's exactly going on with my physical things at any particular point in time, but I then want to take the information from the physical thing at every time 0 and then project it out so that I can see what's going to happen in the future and be able to avoid problems as opposed to simply wait until they happen and then have to fix them. In the physical world, we're constrained by time. It only goes in one direction, and that's forward. Whereas in the digital twin, I am unconstrained. I don't have to operate by the constraints of a physical clock. I can change the clock to be anything that I want. And so we're unconstrained by time in the virtual area in my digital twin. So modeling simulation, models that at every time tx. But what I said before is what I'd like to have is front-running simulation that every time 0 or time x, I can basically be able to predict what's going to happen in the future. So it's my crystal ball into what's happening, and I will contend that at some point in time, every product will have a digital twin running ahead of it to be able to predict performance. But I can also do forensics. I can run the arrow of time backwards if I do it right. There are some constraints in this, and basically be able to figure out what happened from my digital twin if I have collected information. Again, in the physical world, once something happens, it's gone unless I capture it physically. Whereas with the digital twin, I can capture that information and then run the arrow of the clock both forward and backward. So digital twin is unconstrained, and this can be a huge benefit both in preventing errors from occurring and figuring out what did occur when something that was that we hadn't projected was going to occur actually did occur, and be able to uncover what the root problem. So I will contend that we are moving from the digital twin we've had in the past to what I call the intelligent digital twin. And this was outlined in a very recent paper that I published that's available online. And so if I look at the characteristics of a digital twin versus the intelligent digital twin, they have these characteristics. The digital twin of today is relatively passive. I basically have to go out and capture the information, where my contention is the intelligent digital twin is going to be active. It's going to be looking for things that it can help us with. The digital twin today can be offline. I can batch up this information and only look at it when I need to, where I will contend the intelligent digital twin will be an online kind of resource that is going to always be looking for opportunities to help us. We give the goal to the digital twin of today. The intelligent digital twin can do its own goal seeking, and again, it looks to minimize resources. We have to do that in the physical world. It could help us do that with the intelligent digital twin. And finally, while we can predict things if we ask it the right questions, the intelligent digital twin is going to be anticipatory and looking at the probabilities of various things that are going to happen, and being able to warn us off. Two of the big problems that we have as humans is confirmation bias. We only confirm what we think the opportunity is going on, and we also are too optimistic. And so the intelligent digital twin will help us with both confirmation bias and unbridled optimism. What's coming on stream is artificial intelligence. And AI means a lot of different things to a lot of different people. And from my perspective, it ranges from a very smart calculator to the Terminator who's trying to wipe out mankind. And so this whole idea of artificial intelligence is this pretty wide range of how we think about this idea of computers having this idea of intelligence. And so it's on a spectrum from expert systems to this singularity where these AI things are going to think for themselves. I have to tell you, I'm not very convinced about that particular thing, because intelligence, as I've defined it, is goal seeking while minimizing scarce resources. And so this idea of intelligence is this idea that we're basically going to seek goals and we only have a minimum of physical resources to deal with. Quite frankly, AI is in an unusual situation where nature tries all possible combinations and lets the environment sort it out. Because computing capability is so cheap, AI acts more like nature in that it can afford to do all kinds of examinations and it still minimizes resources pretty effectively. We have dramatically different hardware than computing capability are. And somebody recently asked me, how do we prevent the Terminator over there from occurring? And I said, we always ought to have AI that has a plug. And so that's one of the ways that we can control it. They live in a virtual world, and we do have an advantage being in the physical world. What I really want is not the Terminator, but what I want is human assistance, or what I call acute availability, versus the human replacement. And so this is where I think artificial intelligence will be, is our own little angel sitting on our shoulder, telling us that we have to be able to avoid problems, or helping us predict the future. So this is where my perspective of AI is. If I look at occupants versus space type, and the occupants are humans and AI versus space type being real and virtual, in the lower left-hand quadrant, quadrant one, humans in real space are goal-oriented. They minimize resources, physical resources. they have bounded rationalities. They only can think of certain things. They have limited computing capability, but it's context rich. They see everything that's occurring in real space. When we move them over into virtual space in quadrant 2, they still are goal oriented. We relax the resources because now they have access to modeling and simulation that they can control. They still have bounded rationality, but the context is limited because the virtual space is limited. When I move over to the bottom right-hand quadrant, quadrant 3, AI in real space is goal-oriented. We give it the goals. It's intended to minimize resources in real space. It is compute-bound, although, as I hope I've convinced you, the computational boundaries are going up exponentially all the time. But it is context limited. It only has certain sensors that allow us to be able to understand what's happening in the real world. When I get to AI in virtual space, they can be goal-oriented and they can do discovery in an unbounded fashion. And as I said before, they basically emulate nature. They can try all possible combinations. They can explore the entire solution space and be able to assess what meets their goals the best. They still are compute bound, but again, that's going up exponentially. And they're limited in context by the programmatic aspect of how we have programmed the virtual world. So there's some very big advantages that AI has in virtual space and humans have in real space. And our goal is to try to combine those two to get the best of both worlds. So how is the digital twin evolving? If I look at the idea of information evolution, which is both in the amount of information and the richness of that information and complexity against the physical to virtual maturity, it looks like this. We have the traditional way that we've done things since time immemorial as level 0. And that's as soon as we had an idea, it almost had to take physical form at that particular point in time. Either drawings, blueprints, physical prototypes. I mean, we had to move our ideas into physical form pretty much immediately in order to be able to work with it. The beginning of this millennium was a time of transition. And so we started to transition into the virtual world. There are a number of things that happened at that particular point in time. We went from 2D to 3D, which was a quantum leap in our ability to visualize things. IoT happens around this particular point in time. We basically are able to connect the physical and the virtual world. And the digital twin starts at this point in time, the idea that says we can represent the physical world in the virtual world. And so this happened in the early 2000s, and I call that the transitional period. Where I contend is we're in the conceptual period, the ad hoc period. We can create digital twins, but we pretty much have to do them ourselves, and we have to be able to make those connections between the various aspects of the virtual world on an ad hoc basis. And so we have begun in that particular area. My take is we're at the early stages of digital twin, and we're in the conceptual stage that has great promise, but we're still at a very, very early stage of being able to get the maximum benefit out of digital twins. We're going to move into the digital twin platform, and I'm starting to see that happen. You're hearing about metaverses and platforms, and so the idea of replication of the physical world into the virtual world is what we're seeing, and we're basically seeing the ability of having these digital twins come together so that they can do a lot of the work in presenting us that information that we're currently doing on an ad hoc basis. But where I see us going is the intelligent digital twin platform that I'm talking about. So front-running simulation, the ability that every product is going to be looking out into the future and running a new simulation to warn us of the probabilities of things that are going to occur so that we can, in essence, address them before they become real problems. And so this is my idea of the digital twin evolution and where we're going. Again, we're at level 2, we're in the conceptual area, we're in the early stages, but I think that we're going to see some very, very rapid improvements in digital twin platforms, and then in its ensuing intelligent digital twin platform with front-running simulation. So we need to understand that how are we doing in moving into this virtual arena with digital twins in a virtual environment. And so in the early 2000s, I had proposed these tests of virtuality that I called them. And they were modeled on the Turing test. So those of you that saw the Imitation Game, this idea that Turing had that in order to be able to test whether computers were capable of human intelligence is to put an observer in a room and have them talk to both a computer and a person. And if they can't tell the difference between the two, it passes the Turing test. No computer has really passed that. There's some issues I talk about in my paper about why that is. In a lot of cases, it's testing the gullibility of the observer. But the idea that says that computers will have the same intelligence as humans, I think was wrong. And with all due respect to Dr. Turing, I think that we'll be able to model and simulate everything but human behavior. And so the idea that says modeling and simulation is going to basically be able to have the virtuality of everything that's non-human, I think is a possibility. And so the tests that I proposed, there were three of them, and I've added a fourth, is what I call the visual or sensory test, a behavioral test, a reflective test, and a predictive test. And I'll talk about those, each of them. The visual or sensory test, meaning that we could test other senses other our visual aspect. But remember, the visual aspect that we have as humans is our highest bandwidth of information and data that we can get. And the visual test goes something like this, is that we have an observer that's outside of the two environments. And in one, it is basically a video of a physical aspect that we're looking at, a physical product. And then it's a model and simulation of the virtual one. And if they can't tell the difference between the two, it passes the visual test or the sensory test, depending on what you're testing. When I first proposed this, we were getting fairly good at basically being able to see if the visual aspect works. So you can ask for the test to have anything done in a spatial environment. You can have the product taken apart, you're going to put it back together, you can rotate it, you can open the doors of a car and look in. And if you can't tell the difference between the physical and the virtual, it passes that test. You could tell the difference then. Today, we're getting so darn close that I have to keep asking during demo, is that a simulation or is that a video? And so we are getting very, very good at basically being able to get to the point where we're going to pass the visual test of virtuality and not be able to distinguish what is a model and simulation against what is a physical video of what we're looking at. The performance test is a lot harder. The performance test is now, we basically put the digital twin in the both physical and virtual environment, and we can ask to have anything done. We can have power applied to it. We can have a test of how gravity affects it. We can look at heating it up and seeing how it performs. We can do anything in terms of checking the performance. And if the virtual one does the same as the physical one, then it will pass the performance test. We have gotten fairly good in specific aspects. And again, I always drive digital twins from use cases, but to say that we have the ability that no matter what forces we apply or how we have the digital twin generate its own forces, that it's going to basically reflect what happens in the physical world, is we're far from that. But in certain particular areas where we look at particular use cases, whether it be a crash test or whether it be the effect of gravity in a dive and those forces on an airplane, or say bending the wings of an airplane until they break. We are getting very, very good at that, although we don't have a general performance test. We have individual performance tests that I think that allow us to model and simulate the physical world quite well. This is sort of the problem with additive manufacturing, is that we haven't been able to model and simulate additive manufacturing as well as we can. That we have homogenic metals, but we need to basically be able to have our virtual things be able to emulate the physical ones in order to pass this test. The reflectivity test is a test of how well our digital twin instance reflects its physical counterpart in the world. And so what the idea here is that no matter what changes on the physical aspect, if we can see the same changes in its digital twin, it will pass the reflectivity test. Now, again, it's driven by use cases, so we may not have everything that we need. So for an airplane, we may want to know, where an airplane is flying out in the world, actually where it is, which was the problem with the Malaysian airplane. What is its speed? How much fuel is it using? How fast are the engine turbine blades turning? But it all depends on what we're looking at. Is what is going to be the definition of the reflectivity test. IoT has helped us quite a bit, but we still have a fair ways to go in terms of having the digital twin capture all the information that we need from its physical counterpart, no matter where it is in the world. Finally, the last test that I added is the predictive test. And that is that we take the digital twins and its physical counterpart. The digital twin projects what's going to happen at some point in time. And then unfortunately, we have to wait for the clock to tick off all those increments in order to see whether it passed that test. So obviously this test isn't quite as good as some of the other tests, but the whole key of having digital twins is two things. One is, to reflect to what they're doing at any point in time, to be able to interrogate where they're at. But the real advantage is, can we predict what's going to happen to them into the future? If we have models and simulations that don't pass prediction tests, they're fairly useless, and that is unfortunately some of the aspects that we have with some of our models and simulations of complex things such as the environment. But what we need to be able to do is to be able to have a prediction and then have the prediction come true in the physical world. And so again, we have some things that are fairly good at this. Again, we drive it from use cases, but I think we have a fair amount to go. And especially if we want to do front-running simulation, where at every time zero we are doing predicting, we're going to need a lot more computing capability than we have today. Although probably the amount we'll have tomorrow will be sufficient. So I'd like to just start to wrap up by talking about digital twin impediments. What are the problems that we're going to have in terms of implementing digital twins? Executive education understanding is the big one. And the reason here is the executives are the ones that are funding this, and they need to be able to understand what the value of digital twins is and how are they going to add value into the organization. And so we need to basically be able to have them understand that. There's an issue with retirementitis, is that executives looking at retirement may not want to undertake something that they view as risky and will not have the funding for it. So we need to understand that we give them the right education to be able to give us the investments that we're going to need. Hype potential. I mean, the counterpart to that is we hype too much. We overpromise what we're going to do with the digital twin, and we underperform. That is not going to help in terms of being able to get the funding that you're going to need for these particular projects. Organizational culture and inertia. I mean, one of the big problems I view is not technology. It is the fact that people are used to working in the physical world, and moving them into the virtual world is going to be a problem. Testing is one area where people, the testing groups think that you have to do physical tests in order to convince yourself that something is going to behave the way they think it is. We're going to need to basically be able to move the needle in terms of moving those people forward. Some of the help is the digital natives coming into the organization, and maybe some of the more resistant people leaving it, but we still have this particular issue in certain disciplines. Creating value-based use cases, as I said, we need to drive everything from use cases. So creating a digital twin of everything, and you don't know where the value is going to be for that, is, I think, a waste of resources. So honing in on value-based use cases and use cases that are going to create value for the organization, I think is critical. Cybersecurity, I mean, my big issue here is when we have physical things, we can put them in remote places and secure facilities with a lot of walls and armed security around it. When we put them into the virtual arena, we have a whole different problem. And so cybersecurity of our virtual assets and their performance is going to be a critical thing we need to have wrestled to the ground in a very quick fashion here. And then finally, what I call cohesion and integration. The fact that different digital twins don't integrate and we have to do cohesion is an issue that I'll talk about in the next slide. So if we're going to have interoperative digital twins in modeling and simulation, we need to have a thing that I call cohesion. And cohesion takes two forms depending on whether we're looking internally or externally. Interoperability requires cohesion for these two things. Internally, for individual digital twins. So what this means is that if we extend the length of an I-beam, the weight of that I-beam has to increase. In the physical world, this happens automatically with cohesion that's enforced by atoms. When we're in the virtual world, we have to worry about all this programmatically. And so individual digital twins have to have cohesion in their use cases, or else we wind up not being able to mimic the physical world. Externally, if we have multiple digital twins systems, and we have system of systems, we have to worry about cohesion between systems. So in this particular case, I have an aircraft, and it has a fuselage, it has fuel tanks, and it has an engine. And so when I increase the amount of fuel in the fuel tank, not only does the fuel have to increase in that fuel tank, but the weight of the entire airplane has to increase. And so I have to enforce cohesion there. So cohesion enforcement is done kind of in two ways. In the physical world, it's done by material and forces. We don't have to worry about it. If we basically don't take into account gravity and something, doesn't matter. It's going to assert itself. If we extend the length of our physical beam, it's going to automatically increase in weight. In the virtual, it requires information inputs and digital processing. So we have to worry about all these cohesion aspects that we get as a byproduct of the physical world in the virtual world. So we have potential for digital twin cohesion solutions. And in sort of an order of how we have to do them and their cost, it goes like this. We can enforce them with ad hoc custom software. And in point of fact, I've seen some really interesting applications in the oil fields of the Mideast, where they basically have digital twins of their entire oil field from the wells to the pipes to the refineries, and they have taken all the different digital twins and have programmed them. Very expensive, but they've gotten pretty amazing returns on their investment by doing this ad hoc custom software. We can go to standards, ontologies, attributes, method call, semantics, okay? The problem with standards is they take a long time, and a lot of times they're rife with political issues. And so So while they are good and we're starting to see some of these, it's a ways off to before we can say we can rely on standards for digital twins that can connect to each other. Harmonization. If we get different organizations who are developing these things to be able to agree on that, between those organizations, we can have integrated digital twins. But it's going to require people working together nicely in the same sandbox in order to be able to do that. Middleware. So middleware is sort of like ad hoc custom software, but it's somebody who's going to do a bunch of these things in order to be able to provide us with that capability. It's happened over in ERP. I expect to see it happen in digital twins. And platforms are where I see us going. So platforms, metaverses, whatever you want to call it. Concerns me when people who are developing metaverse, who I will not name, that says, yeah, you really don't have to worry about all the modeling of physical attributes, and we don't have to have great fidelity with the physical world. I mean, for digital twins of things that we're doing in this particular area is important. For games, not so important. For digital twins of airplanes, rocket ships, health products, it's going to have to, the platform is going to have all the aspects that we're going to need of the physical world. So if you're interested in sort of my perspective on things, here's a list of selected publications in terms of both digital twins and their impact in the life of a product. And these are pretty readily available for the most part out on ResearchGate. And with that, I'd like to thank you for your attention, and I invite you to have a great conference for the next couple days. Thank you. Bye.